Awesome. Well, it looks like I'm the first talk in the session today. That's amazing news. That means I still have everybody's full attention, hopefully. So, welcome to Generative Camera Dolly, Extreme Monocular Dynamic View Synthesis. My name is Basile, and I'm very excited to present our work here to you today. First of all, what is a dolly? It might be a little bit of an uncommon word for some of us. Perhaps it reminds you of an image generator with a similar sounding name. But my prediction is that once you figure out the meaning of this word, your reaction might look something like this. Because this effect is called a dolly zoom, and it was created with a camera dolly, unsurprisingly, which is basically a platform on wheels used in filmmaking to create smooth camera movements over time. But wouldn't that be cool if you could do away with all of this equipment and instead perform visual storytelling with the help of computer vision? So given any video, what if we build a model that is able to reimagine and reproduce that scene from a different perspective? We also want to be able to freely choose and control that viewpoint after the fact, as if we were operating a virtual camera dolly. So the end goal is essentially to capture and understand the dynamic 3D environment based on just one input video. This idea naturally falls under the umbrella of novel view synthesis, and I'm going to simplify a little bit here by saying that the existing work here can be broadly divided into two categories. On the left, we've seen a lot of amazing progress recently in image to 3D or novel view synthesis for objects. So given a single input photo, these models can generate images of all the different sides of that object for a downstream 3D reconstruction. And on the right, we have the time dimension. So we have dynamic view synthesis for scenes. Most of these methods carefully and iteratively optimize a tailored 4D reconstruction, after which they can render high-quality videos from novel viewpoints, albeit with relatively limited camera viewpoint displacements. And don't get me wrong, these works often have detailed and impressive results, but since they mostly train for each scene separately, it makes them a bit slow, and it also prevents them from learning generalizable priors or useful knowledge about the physical world that can be shared and transferred across different examples. So the natural question is, can we do something in between that somehow combines the best of both worlds? Specifically, how should we accomplish view synthesis for dynamic scenes based on a single video that takes less than a minute and works for more extreme perspective changes? This is a very tall order if you think about it. And I want to share two important thoughts with you at this point. Number one, we're going to need precise camera pose control. Right? If we model this problem in an end-to-end fashion without intermediate 3D geometry, then we still need to properly condition it on these camera transformation parameters. Number two, this is at its heart a video-to-video translation problem. And today, in the age of generative AI, we all know what the state of the art in visual synthesis is, right? The answer is obviously GANs. Just kidding, it's diffusion models. And we also know that modifying diffusion models in order to teach them new skills, such as ControlNet or 0 to 3, has been proven to be, and still is, a very fruitful paradigm. So, to turn this dream into reality, we take a state-of-the-art open-source generative video model, in this case stable video diffusion. We modify it to accommodate the new types of conditioning that we need, which are camera matrix and the input video from the source viewpoint. And the core idea is then that by training not from scratch, but instead from the provided image-to-video checkpoint, we establish the roots of our framework in these, basically in a very large-scale pre-training stage that happen on all kinds of video data from the internet. And then we conduct those priors towards this new task that links together videos from different synchronized camera viewpoints with each other. That was a whole mouthful. So this whole thing is trained on multi-view video, and we contribute two different datasets in this context. The first one is based on the Google Kubrick simulator, with many dynamic objects undergoing various complex motion and occlusion patterns. The second one is called Parallel Domain, which is also synthetic and has thousands of high-quality, diverse driving scenarios from 19 different viewpoints. Let's take an initial look at some results on the test set. In each case, we choose a set of angles randomly. So there's 4 different examples shown here. And then we ask the virtual camera to gradually rotate or move towards that desired perspective. And I'm not going to pretend that these results are perfect, because they're not, right? But if we think about the extremely difficult nature of the task, it basically implies solving video to 4D to some degree. I think the results are definitely decent, and the geometry and the appearance and the dynamics of the objects are mostly well preserved. We also compare against several baselines. First, in our model on the right, you can see that despite heavy occlusions, particularly the brown container in the middle, all the objects remain reasonably consistent across views and time. On the lower left, we have 0 and VS, which is roughly speaking 0 and 3 for scenes. And we observe flickering, because this is for image to 3D. It has to handle every frame independently. On the lower right, we have hex plane, which is roughly speaking a more efficient version of dynamic nerve. We observe many artifacts and incorrect geometry, because the problem is far too under-constrained for a model without strong priors to overfit to the scene from a single viewpoint. In fact, we found that hexplane has to have about 16 contemporaneous different viewpoints available to reach a similar performance as ours, which is from just one viewpoint for clarification. Let's turn to the real world. If we look at the input video on the left, both the blue and the red ducks are getting fully occluded. This is, of course, related to object permanence and intuitive physics, which are very challenging, very interesting problems in computer vision. So I think it's very cool that our model predicts the correct result here, because it suggests that it actually learns the necessary spatiotemporal reasoning skills in order to estimate the 4D scene content as well as possible. Some more real-world examples are shown here. Imagine you are a robot and you want to see what the consequences of your actions are. Well, then it makes sense to use our model and predict these other viewpoints in order to basically maximize your situational awareness, for example, as you're actively manipulating the scene. Here are simulated driving scenes, where we shift the camera mostly backwards and upwards. And with our framework, we can predict either visual colors or semantic categories. Right? And even though some artifacts are visible, the results are still quite solid, because when you look closer, you'll notice there are many total occlusions going on between the different objects in the scene that are often reconstructed correctly. It also works on real driving scenes. It also doesn't work on real driving scenes. This is probably my favorite failure video, because if you count how many cars are being predicted on the right versus how many are in the input on the left, there are actually none at all. So I don't know what the model was thinking here, but the point is that we're still far from solving a zero-shot generalization in terms of video to 4D or dynamic view synthesis. So to summarize, this was generative camera Dolly. We devised an approach that conceives a virtual camera that moves around freely based on just a single physical camera. And I think there are many promising future applications here in terms of, for example, building better 4D scene representations, learning word models for embodied AI, possibly even VR or spatial computing. We also publish high-fidelity multi-view video data sources. And because our approach is basically surfing on top of state-of-the-art generative models, there are very good reasons to believe that it is scalable, and we will keep improving over time along with the quality of the underlying representation, as well as everything else, so the size of the model, data, and compute capacity. Please feel free to check out our webpage for many more visualizations, including more failure cases, as well as links to source code, data sets, pre-trained models, and so on. I did skip many details in this presentation, so please feel free to come by our poster at number 156 if you have any questions, and I'm looking forward to the discussions. Thank you so much to all my collaborators and to you all for attending.
Is there any questions from the audience? There are microphones along the aisles. Please come. Oh, yes.
Hi, thank you for the amazing talk. So my question is, did you experiment with different video diffusion models, and how much does the output quality of your method depend on which model do you use?
That is a great question. So it would have been, I think it would be great to sort of know these scaling characteristics, right? Like what if you use better versus worse diffusion models? How much does that affect the results? In our case, we just chose to go with stable video diffusion because that was sort of a very good state-of-the-art open source generative video model. And yeah, it already took a little bit of effort to get fine-tuning there to work. So we stuck to that, and then we decided to run experiments along the other factors of variation instead.
Any other questions? Yeah. If not, I will ask one question. So you mentioned about you learned the dynamic scene, right, for novel view synthesis. Is there any physics that is being learned inside here? Because you also show examples of the robot and the scene interaction.
There is no explicit physics priors that we're applying or inserting into the model. I think as a result of that, the physics capabilities are not amazing, right? The dynamics, sometimes you can see that the objects behave in like slightly unnatural ways. I think it would definitely be interesting going forward to see whether that can be solved with more scaling or by applying priors in some way. But yeah, this model is just end-to-end, video to video. So there's no explicit physics priors.
Okay. Yeah. Okay. Is there any other questions? Yeah, if not, then let's thank the speaker again.